we will look at Faraday's law in the integral form, and then we will try to solve some of the problems coming out of this. So Faraday's law. I gave you a preview of this in one of the previous videos. Give you some of the concepts. I'll restate the concepts now. Let's start with the Faraday's law. So what we have is EMF, or electromotive force, or voltage set up in a loop, is equal to minus, and then you have the derivative here of the magnetic flux with respect to time. And we will ignore n for the moment. Normally you would have here, normally this would look like this. You'd have minus n d phi of dt, but we'll only look at a single loop. So this goes away. And then let's dig deeper into this. So this is the expression for EMF that we have. Now flux, let's do the flux first. So the flux, magnetic flux, that's V dot dA, where this is the surface integral through some surface, right? Through some surface, and what surface are we looking at? Well, we're looking at a loop. Because what we have is a loop. We have a loop, a coil here, a single loop, and magnetic field points through this thing somehow. So let's say that the magnetic field through this thing points like that. Here's B, and then here's vector A. A points like this, and you just find, by doing the dot product over there, you're finding how much of the magnetic field is pointing through the surface, but how much, really what you're looking for is what is the projection of B on A. But anyways, so we find the magnetic flux doing this little calculation. So you could already express this equation slightly differently, and that is you would have d dt of the integral here, B dot dA. So this is a surface integral, and you integrate this over some surface S. That surface S would be the surface of the surface enclosed by the loop. So you're looking at, this is the surface S. This is surface S, and it's enclosed by this black loop here. All right, so that's the right-hand side of the equation. The left-hand side of the equation, EMF is like the voltage. You can think of it this way. And if there is in fact a changing flux, magnetic flux here, so what I'm going to do is, let's say that there is a flux, magnetic flux that is not constant. So this thing is not constant. That implies that there's a certain EMF in the loop, meaning there is a certain voltage. And so you could redraw this picture, and it would be true to redraw it in this way, because you're just modeling the behavior of the charges. And so you'd have, as if you had a voltage here, that voltage, some kind of an EMF, and then you had this thing coming around some resistor R, where this R would just be the resistance of the wire here, and then this thing comes back to the battery, and so you set up some kind of a current flowing, right? If you have EMF, then you have current flowing in this circuit, and so there's some kind of a current I that flows through this. But here, the current is due to changing flux. Here, the current is due to the battery, but the two pictures are functionally the same. Now you should recall that there is an expression for EMF. If it's just the voltage, then that is simply E dot dL. And so the equation we used was that the electric field was delta V over delta D. The average expression for the average electric field value at some point in space was delta V over delta D. This really should be, the proper expression is that the electric field there should be a negative here, if I remember correctly, and then this is a gradient of V. These are kind of the same expressions in a way. And from here you could end up with, so from here you could end up with this. Now, where does the electric field come from? We've been working with magnetic fields and currents and voltages. Suddenly we have the electric field. Where is the electric field coming from? Well, if you have a bunch of charges here in this loop, and you do, you have a bunch of charges because you have a bunch of atoms that comprise the loop. You have a bunch of positive charges all over the place here, and they move, then there must be force acting on them, right? These charges couldn't possibly move unless there was a force pushing them. So there must be some kind of a force that pushes them. And it is this force that gives rise to EMF, right? It's because of this force, presence of that force, that you get EMF. And so that force, well, if you have a force here and the force acts on charge Q, then you may recall that force is equals Q times E. And so you should have some kind of an electric field present here. And in fact, you do. So on the left-hand side, so let's leave this thought for a minute. Going back to this equation here, what I can write on the left-hand side is that instead of EMF, I could write E that dl. But it's, you know, dl of what? We're looking at dl being these little elements here. So this is a little element dl, dl, and you keep going around in a circle. These are all of your elements dl. All right, so these are your dl's. In other words, you're integrating over the surface here, over the edge of the surface as, and that equals to minus d dt, and then you have b dot dA s. So maybe what I'll do is let's indicate this as here in white, and now let's draw the surface. So what we have is this, the surface of the loop, where we have the wire. When you do the right-hand side of this equation, you're considering this element dA, and so you're actually integrating over the entire area here of this loop. So this is your surface. This is the area of A of surface S. But on the left-hand side of the equation, when you do this line integral, what you're doing is, yeah, you're adding up all of these little dL's around that area. So what you get here is, well, these are your dL's, right? So this S here is related to the other S in that they're both the same surface, but on the left-hand side, you integrate along the edge of the surface. And on the right-hand side, you integrate through the area of the surface. Right. Now, you could take this equation. This is the Faraday's law, one of the Maxwell's equations. You can take this equation and you could do the following with it. So let's dig a little deeper into what's happening here. Let's say that you have a magnetic field, and the magnetic field points like this. So here's the magnetic field, and then let's say that this magnetic field varies with time. So let's say its magnitude varies with time, and so what I have is that this somehow belongs it's some kind of a function that depends on time. So it maybe increases, maybe it decreases. So that implies that you would have, if you look at the right-hand side of Faraday's law, d dt of b dot dA, if nothing in this equation here varies with time, then this whole thing becomes 0, because ultimately you're taking the time derivative of this whole expression, right? So if nothing in here varies with time, then you end up with 0. But if something does vary with time, then you do not have a 0. And in fact, in the specific case that I'm considering now, the magnetic field does depend on time. And so this whole right-hand side is not 0. But if the whole right-hand side is not 0, then the left-hand side is not 0 either. And so what I have is E that dl is not 0 either. It just follows directly from the top. But if E dot dl is not 0, then, well, let's make up some surface here, because this is done over some surface. This is done over some surface. So let's make up some, here's a surface. And the electric field is integrated along the edge of that. In other words, the this line integral of electric field along the edge of the surface is not zero, that means that I have electric field along this edge here. There's a circular electric field that looks like that. Now suppose that I pick a different surface now. Let's say I take a different surface, maybe this surface here. And if I integrate along that surface there, then what I get is, well, again, if the right-hand side of the equation is not zero, then the left-hand side is not zero, but here I'm doing the integral of E dot dl. What I get here is that along this path here, electric field is not zero, and so I have an electric field here. And I could pick any other surface that I would want. It doesn't have to be circular. I could pick some kind of I could pick a square if I wanted to. Right, here's the surface, and I'm going to, the magnetic flux through the surface varies with time. Magnetic flux through the surface varies with time, and so what I have is, that implies that the right-hand side of the equation is not zero, but if right-hand side of the equation is not zero, then the left-hand side of the equation is not zero. But the left-hand side is just the dot of E and dl, and so what I have is that if I do E dot dl along the surface here, I don't get zero, and that means that there's an electric field present here. That doesn't mean that the electric field is actually along this edge. It doesn't have to be. It could be pointing like that, it could be pointing like this. Right here it could be pointing like that, here it could be pointing like this, but here it could be pointing like that. But E dot dl is not zero. So what you should draw from here is that if you have a magnetic field, and the magnetic field, let's say, points like this, and this magnetic field varies with time, then from this you end up with flux varying with time, or rather you would have the, do I want the, let's use the black. From here, ooh, where did we get that color? There we go. So dt of the flux, E dot dA, this is not zero through any surface here, and then you would get what that gives you. Of course, there's a negative sign here. You would end up with E dot dl is not zero, and so that means that there is an electric field present. So I started here. If your magnetic field is changing in time, then through this equation here, you end up with there is an electric field present. And depending on how this, oh, I think I know what happened with my red color. Oh well, if the there's the Lenz's law that you could use to figure out the direction of this electric field. But anyways, if there's a changing magnetic field, then you have an electric field, and in fact, the electric field would just be would be curling around around the magnetic field. And if you move out, it would curl this. And if you moved out a little farther, you would have this magnetic electric field just sort of doing the same thing. That is, it would just point like this, and so on. Point is, and then I could add another one if I wanted to. So here's another line of the electric field. It would be circular electric field. Note that here you have an electric field. Actually, that's kind of neat. Let's show it. Let's extend this thing a little farther out this way. And then let's add something to it. So now let's, if I'm here, I would have this electric field that does something like this. And if I were out here, I would get it like this, pointing like that, and it just loops around and so on. Note that you have electric field even though you have no charges present. So this electric field is a little different. It's the same as the electric field due to a charge. So if you have a charge, you have an electric field. But it is a little different because there is no charge setting up this electric field. What sets up this electric field is a changing magnetic field. And it kind of works in both directions, in a sense that if you have a changing electric field, there's another equation, Maxwell's equation, that shows this, but if you have a changing electric field, you end up with a magnetic field, and likewise, if you have a changing magnetic field, you end up with an electric field. So the two are inseparable in that sense. Electromagnetism is one thing, with sort of two different aspects, electric fields and magnetic fields, but they really are one. If you have changing magnetic fields, then you have magnetic fields as well. And if you have changing magnetic fields, you have electric fields. That are inseparable. Anyways, here's the concept, here's the equation. So now let's go ahead and try to solve some problems.